Domain, the basics and beyond. The domain of a function f of x is the complete set of x's that work. All right? So for lack of a better word, I used work there. All right? So another way to put it is all the x's such that f of x, when you plug in the x value into the function, that value exists. Okay? Basically, it's what you plug into the function that yields a valid result. Meaning you can't get undefined or something that, square root of a negative for real numbers, that kind of thing. The complete set of all the possible results is called the range. Okay? And then for the function f of x equals y, x is the domain and y is the range. So basically, and this is the basics part, there are two major issues when you're just talking about functions that you kind of see all the time. And those two issues are rational functions and radical functions, or even roots more specifically. Okay? Those are the two big issues when you talk about restrictions on your domain. Now, the deal is there are other possibilities like piecewise functions that may also cause restrictions to the domain. So this video will only explore the two listed above as an introduction to finding the domain of a function algebraically. Okay, so the basics part is we're just focusing on these two things. The and beyond part, really, I talked about range a little bit here, and then near the end of the video, I'm going to combine these two things where I have a fraction, a rational function with a square root, an even root in the denominator or the numerator or whatever. And so then how do we put those two things together kind of thing. So that's the sort of and beyond part here. So it's not really way beyond, but it's beyond a little bit more than just the basic thing. All right? Domain is typically expressed in interval notation. The domain of a polynomial is all real numbers. So if I have only x powers that are whole numbers, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then that's a polynomial. The coefficients can be fractions, decimals, square roots, whatever, but not the powers of x. The powers of x can't be in the denominator, can't be negative. So here the domain is negative infinity to infinity. Another way to write that is this r. And so when I write it, this r right here, I write with two lines like that. Or r, well, I can't write. R with an extra line through it, okay? That doesn't even look, I don't curl mine in the center. That's what mine looks like, okay? So, but an r with an extra line through it. Rational functions, the restriction is due to the fact that the denominator or the bottom what? Can't be 0, okay? So then the process step, this is what I call it. I call it the process step. I have to identify whenever someone says find the domain, the first thing I do is say, hey, is there an x in the bottom? I know the bottom's not the right word. Is x in the denominator? If there is, then I have a restriction. Or is x under an even root? Then I have to worry about a restriction there. Even root. Odd roots are okay because you can take the cube root of a negative. You can't take the square root of a negative. So what I do is I set the denominator not equal to 0. I don't know that I've seen a book do this. I can't remember. I've taught out of several books over the years, but most books say equal to 0 and you find the number that's left out of the domain. I put not equals to because it reminds me, hey, I can't use this number. Okay? So I do not equal to 0. I do this here. I do this when I look for vertical asymptotes, even though the asymptote itself is equals. I'm reminding myself, hey, this number can't really work for this function because it would make the denominator 0, or these numbers. Radical functions, even roots now, not odd roots, even roots, so square root, fourth root, sixth root, eighth root, 10th root, that kind of thing, even the 52nd root. The restriction is because the radicand, and the radicand is fancy word for what's underneath the radical. What are you taking the square root of or the root of? It can't be negative, which means it is, if it cannot be negative, what does that mean? And a bunch of y'all are going, positive! Nope. Positive or what? 0. So it's greater than or equal to 0. If it cannot be negative, it's non-negative, then it's greater than or equal to 0. So then guess what my process step is going to look like on this one? My process step is going to be to set the radicand greater than or equal to 0. Again, just drop the radical off of it. It doesn't matter what else is there. Drop the radical off of it and then say that has to be greater than or equal to 0. And that may be part of your domain. You may have to do some other things if the rest of it has something else like a fraction or something else in it. So here, let's find the domain of the following functions. Put your final answer in interval notation. So look at g of x. Little g of x, 4x to the third plus 95x squared minus 13x minus 111. If I look at this, the first thing I ask myself, are there any x's in the bottom denominator? The answer is no. Are there any x's under a radical, even root? No. So this thing, is it a polynomial? Yes, this is a polynomial. Because all my powers, 3, 2, 1, and then x to the 0 here, all those powers are whole numbers. So it's a polynomial. So then the domain of G, that's how I usually do it, domain, abbreviate and put a G, and then is what? Negative infinity, comma, infinity. So I would accept this answer. And look, put your answer in interval notation. I'm going to use the word all, but I might be misremembering. As I've gotten older, I mix memories up now and that kind of stuff. I don't recall a teacher or professor, instructor that I had or that I've worked with who would not accept this answer as well. So I accept that. I don't like you writing the words all real numbers here when the directions say put your answer in interval notation, although I have even allowed that. It's not technically interval notation. This symbol is widely regarded in math to be the same thing as this, so that's why I feel like I've never run across anybody who didn't accept that. Now, again, that doesn't mean your professor won't. I've only worked with a very small fraction of people out there. I mean, I've been at 7 or 8 places in my career and worked with a lot of people for what I do, but, I mean, there's way less than 1% of the teachers out there that are even out there, have I ever even met. So, and that's even just in where I live. So, around the world, a fraction of a percent. So make sure you know what your instructor, professor, teacher will accept and will not. For me, I will accept either one of these, and probably if you wrote all real numbers, I could live with that, even though it's not technically interval notation. All right, so little p of x equals the square root of 7x minus 35. So if we look at this one, is x in the denominator? Nope. Is it under an even root? Yep. This is a square root. So what is my process step? So I'm looking for the domain of p, right? So I want to come over here and I want to box that over here somewhere. But how do I find it? Well, the process is to take the radicand and set it greater than or equal to 0. The radicand and set it greater than or equal to 0. So drop the radical. That's the radicand is underneath it. Get rid of it, and then greater than or equal to 0. Now this is just a regular inequality you solve. Oops. So then 7x is greater than or equal to 35, and then we divide by 7, and x is going to be greater than or equal to 5. How do I do that? Well, on my number line, and some of y'all don't need to do this, but I'm going to go ahead and go through all of it. Greater than or equal to 5 is to the right. Shade that arrow, that's infinity. This is a bracket, and so this is going to be bracket 5, comma, infinity. That's your domain of p. So domain of p is bracket 5, comma, infinity, parenthesis, and there's your domain. Right? So if I wrote this over here because on my test, if you're in my class, I always have an answer box for you to put the answer in. Unless it's a multiple choice final or something, then it has the answers there right for you to choose. But my test, I generate just unit test, chapter test, whatever you want to call it, answer boxes. Here we have d of x equals 5 over x squared minus 3x minus 28. So here we ask ourselves, look, is there anything that can restrict the domain, anything that causes us issues? And we look and we say, wait a minute, we have all of this in the denominator. And when we have a fraction, we know we cannot divide by 0. So the process step, when you have a fraction, when what I mean is x is in the denominator, then the process step, when you want to find, let me write it over here, the domain of little d, and this thing's giving me issues here. When you find the domain of little d, then you say x squared minus 3x minus 28 cannot equal 0, right? The denominator cannot equal 0. That's your process step, right? So you have process steps for denominators. Then if you look down at the problem below, you have an even root. That's a process step, not greater than or equal to 0. But here, the denominator cannot equal 0. So we need to factor this as x squared. This is something I call list method, 3 terms, no GCF, and a 1 in the front. One of my students a few semesters ago named this, and it's just sort of stuck. So what I mean is make a list of the factors of 28. 1 in 28. 2 and 14, 3 doesn't work, 4 and 7, 5 and 6 don't work. So I want the factors of 28 to subtract to give me 3, and I'll come back with the signs in a minute. So that's going to be 4 and 7, right? So we have here x and x gives me x squared, and then 4 and 7, and it doesn't matter what order you put those in. All right, and then we say, okay, the bigger number, when it's a minus here, they're different. So you say bigger number gets this first sign. Well, which one's bigger? 7. 7 gets the minus, so 4 gets a plus. They get different. The only way to get a negative 28 is to do that. So if you have trouble factoring, go watch my list method video. It will tell you how to do that, and it works every time. That's why it's so glorious and wonderful. All right, so then x plus 4 cannot equal 0 to keep solving here. And I used to put or, but I had an English student who told me that it should be nor, and I can barely speak the English language, so I just listened to them and figured they knew what they were talking about, because I don't. All right, so x plus 4 is greater than or equal to 0, nor x minus 7 is greater than or equal to 0. I'm sorry, not greater than, not equal to. X plus 4 is not equal to 0, nor x minus 7 is not equal to 0. So to solve these, subtract 4 from both sides, so x cannot equal negative 4. And over here we're going to add 7 to both sides, so x cannot be 7. So we have two numbers here that x cannot be. Now normally I don't draw a number line when it's in this case, but this sort of helps me see what's going on. If I draw my number line down here, I can have two numbers that concern me, right? Negative 4 and 7. Now I have to put them from smallest to biggest. You don't put 7 here and negative 4 here, that won't work, right? You got to have the smaller number, negative 4, on the left and 7 on the right of negative 4 for this to work, because, right, they go in order from smallest to biggest. So what happens is we want all the numbers in here, we want all the numbers in here, and we want all the numbers out here. We don't want this one point and this one point, right? And we don't use open and closed circles, but I'm illustrating my point here. So we want this interval that goes from here all the way back out to this arrow, and this arrow is represented by what? Negative infinity. Then we want to pick back up right here with a parenthesis into this one, right? Why are we using parentheses? Because we don't include those points, right? That's what parentheses means in interval notation. Then we pick back up again here to get all this and go all the way to this arrow, and that arrow represents infinity. So we have 1, 2, 3 intervals, right? We have 3 intervals here. So what are my 3 intervals? How do I write them down? Well, look, we have it negative infinity. So negative infinity up to negative 4. And that's going to be parentheses, always a parenthesis around infinity and negative infinity. And then negative 4 here has a parenthesis because you're not including it. Then we have a union. And we have negative 4 up to 7. And then union 7. And I almost didn't leave myself enough room up to infinity. So that is my interval notation. Okay? That's my interval notation. And let me say a couple things about this. One is with software packages, whether it's MyMathLab or Hawks or whatever, and I've seen this over the years with my students, they'll send me a screenshot, or they'll send me the thing and say, Mr. Guest, it's counting it off every time, and I know I'm doing exactly what you're doing in class, and I just can't figure it out. And so I look at it and go, man, that looks right. And then I go, oh, wait a minute, right here. What did you use? Did you use the union symbol that the software provides, or did you type in a capital U? Okay, because note the union sign is down and up. It is not this. No kickstand or whatever on the U there. Okay, don't come back down for the U. It's just down and up when you write it. But when you're choosing it in software, there may be a ribbon at the bottom, or maybe on the side, or maybe a little button like it comes up with a calculator. It may even be where it says more symbols or more math stuff, and then you choose the union symbol that they provide. It is often not quite as bold as a letter and a little bit wider sometimes than maybe the U would look in the software packages that I've seen, and I've seen several of them over the years. It's always been something like that. So you want to make sure you're choosing the actual union symbol and not typing in the letter U, because it won't work. And if you were writing it, you would definitely not want to do that. You do not want the kickstand on the U there. All right? So, let's see if I can, well, I'm not going to be able to get that off there. Do it like this. Then the other thing that I want to say quickly is, notice that this is a little d and this is a capital F for these problems. you can't say, like on this next one, I can't go, oh, let me do the domain of little f. Nope. Math is case sensitive. Okay, so this is domain of capital F for this one down here, okay? So we'll come back and do it in a minute, but I wanted to say that you couldn't use a capital D up there. In fact, there's some things in math and science that have a capital R and little r in the same problem, or capital F and little f, or capital D and little d, or whatever. So you just got to be careful that you use what is there. So I chose a capital F on this next one on purpose so that whenever I talk about the domain, I got to talk about the domain of capital F, all right? So on this one, is there anything that would restrict my domain? And I say yes, because I have an even root right here, right? I have a square root 2, right? Even root. So when I have an even root, the process step is x plus 6 is greater than or equal to 0. So when you have a fraction with x in the denominator, the process step is not equal to 0. When you have an even root, it's greater than or equal to 0, because you can't take the square root of a negative, right? Not in real numbers. So this is a real number, real valued function. So then how do I solve this? Well, I'm going to subtract 6 from both sides. X is greater than or equal to negative 6. So then on my number line, I care about what? One number, negative 6. Which way is greater than negative 6? It's out here to the right. And again, I shade all the way to my arrow. My arrow represents infinity. What goes around negative 6 here? It's a bracket, because it equals, right? If you equal a number, it's going to be a bracket. So we have bracket, negative 6, comma, infinity, and that's a bad infinity, so I'm going to come back and do it again. Okay? So then there's your domain here. So we're going to have bracket, negative 6, infinity. And look, I'm going to erase this, and I'm going to do it instead of my fancy technology. I'm going to erase it because I didn't like it, whether it be that or something else. Because in math, we always use a pencil. Always, so we can fix it. Okay? Because even me, as you've seen, I can make mistakes too. I'm human. We all do. So we use something we can erase. We don't use a pen in math. We use a pencil. I can hear math teachers everywhere applauding, screaming, yelling, cheering like their team scored a touchdown. Or in the World Series, their team just hit a walk-off grand slam. Okay? This is good stuff. Use a pencil in math. All right. The other thing I want to say about this is, let's say that you were writing this answer down and you wrote down, negative 6 infinity, and you wrote a parenthesis. And then you go, oh, wait, look, I wrote a bracket over it. You need to make sure you know what your teacher accepts and doesn't accept, but I will tell you this, in my class, I would count that off every time, because otherwise you could just write it down and go, oh, you get it right. And you go, oh, Mr. Guest, but I made it darker. The bracket's dark. No, it's not darker. You used the same pen or pencil to write it with. Better be a pencil. You use the same writing utensil to do the bracket as you did the parenthesis. What do you mean darker? It's the same. I know you may have written over it 2 or 3 times. I don't care. You can't write them both down. I'm not going to give you credit, okay? Otherwise, you could do it every time and get it. So just make sure you know what your teacher, professor, whatever instructor does or accepts. All right? Little w of x equals 4x minus 101. This thing is a polynomial. Not only that, it's a line, but it's a polynomial. And if it's a polynomial, right, there's no x's in the bottom, no x's are in the denominator bottom, and none under a radical even root. So the domain here of w is negative infinity, comma, infinity. And the other way I said I would take that is with the r with the extra line through it, okay? Either one of those. So that right there, I call that inspection. I don't necessarily want you to write down the word polynomial every time, although if you did that, that would let you, your instructor, your teacher, your professor know, hey, guess why I wrote negative infinity to infinity? Because I thought that was a polynomial. All right? So, but that's what's going on. I call that by inspection. You inspected this, and you did not find a rational, x in the denominator or bottom, and you did not find a radical, x under an even root. All right? Even roots matter because you cannot take the even root of a negative number. Odd roots you can. Cube root of negative 8 is negative 2. It works out. But the square root of negative 4 is not a real number. It's imaginary complex. So for real number, real valued functions, it doesn't work. So k of x, little k of x, equals 1 over 5x minus 20. So I'm looking for the domain of little k. What's the deal here? Well, it's a fraction, right? I got x's in the bottom or denominator. So the process step is to take 5x minus 20 and say it cannot be 0. So you can do this a couple of different ways. You can factor. You can move. I'm just going to move the 20 over. I mean, this is just linear. There's no. I'm just going to move it over. linear meaning x is to the first power. 5x cannot be 20, and then divide by 5. So then x can be anything in the world but 4. So what that means is if I do a number line again, I'm taking the number 4 and I'm basically chopping the number line right there. I got an interval on this side of it and an interval on this side of it, okay? And I'm going all the way out, to negative infinity, right? So I'm going all the way out. I got 1, 2 intervals. You always have one more interval than numbers you leave out if all you're doing is chopping it up with a fraction, right? And what I mean is if all you have is x is in the denominator and you don't have a square root or piecewise or anything else messing it up, you're only going to have one more interval, or you're always going to have one more interval than the numbers you leave out. So if I leave out 4 numbers, I have 5 intervals. I leave out 7 numbers, I have 8 intervals. I leave out 1 number, I have 2 intervals. I leave out 3 numbers, I have 4 intervals. So here I'm leaving out one number. So what does my domain look like? Well, it's parenthesis negative infinity, because infinity and negative infinity always get a parenthesis, comma, 4. This gets, and all these are what I call chain linked together with parentheses and a union. So 4 has a parenthesis, union, parenthesis, and pick back up at 4. Chain linked together is what I call that, all right, with union and parentheses. So I have it there, and then when I pick up at 4, do I cut it off again? No, I keep going all the way to infinity. So that is basically everything in the real numbers except what number? 4. All right? And I have seen teachers, professors, instructors use, some sort of R with the extra line through it, and then sort of a slash that means not or take away, and then in the set notation, the number 4. So I've seen it in books. I've seen it on software. So just know that it's possible your teacher may want you to do write it a little different. But interval notation, this is what interval notation is here. So this is the way that I write this. So negative infinity to 4, union 4 to infinity. So f of x equals 2x squared over 3 minus 1.7x plus 6. So I have a fraction, but are there any x's in the bottom? No, I have a decimal, but it's not as a coefficient of x. Remember, it's the powers of x that matter. This thing is a polynomial, okay? Because the powers of x are whole numbers, 0, 1, 2, 3, 4, 5. No negatives, no fractions, which would be radicals. So guess what? The domain of f is all real numbers. And then we get to the and beyond part here. This is the and beyond, because look at G. Capital G, that is. Right? That was little f of x. We saw capital F of x earlier. Here, little g of x, big G of x. I'm sorry, we saw little g earlier. Capital G of x is x squared plus 1 over the square root of 2x minus 7. Oh. So this not only has a fraction with x in the bottom of the denominator, it's also got a radical, an even root with x under the even root. And that's in the bottom of the fraction. Holy cow. All right? So let's take one thing at a time. What does my fraction say? Because that's what I said first. So what does my fraction says? Look, and I like to do this. I say that's my bigger function. The square root is inside the fraction. If the fraction was inside the square root, it would be different. But here, the fraction's the bigger thing. So, and it really doesn't matter. You're going to kind of take you're going to take the intersection of the two. But we're going to look at this and go, okay, look, we need to say that for the process, for when we're looking for the domain of capital G, okay, we need to say square root of 2x minus 7 can't be 0. Right, that's the denominator. That's what I wrote down for my process step. Set the denominator not equal to 0. I didn't do it formally with, a lot of times I see books with n of x for the numerator and d of x for the denominator and say d of x is not equal. I could have done all that, but just the denominator. Well, there's the entire denominator not equal to 0. Wait a minute. I also can't have a radical, right? Or not an even radical. That gives me another restriction. So my radical says take what's under the radical and say greater than or equal to 0. But wait a minute. I can't equal 0, so it just can be what? Greater than 0. Because of the can't equal part, I have to drop the equals. You with me? It's in the denominator. The denominator can never be 0, so if you have a radical in the bottom, it's only greater than 0. You're putting the two restrictions together, right? You're putting the two restrictions together. So now you go to solve this. We're going to add 7 to both sides. We get 2x is greater than 7. Divide both sides by 2. And x is greater than 7 halves. So then on my interval notation, or on my number line, I have 7 halves, and it's going to be out here to the right. That's infinity. And we have a parenthesis this time, okay? And somehow a dot just popped up on my screen. So 7 halves, comma, infinity. So we have parenthesis 7 halves, comma, infinity, which always gets parenthesis, and there's your interval notation. So 7 halves, comma, infinity, but parentheses on the 7 halves because it's in the denominator, and it can never be 0 there. Okay? So look at capital R of x. Do you have x's in the denominator? No. Do you have a radical? Yes. Is it an even root? No, it's a cube root. It's a cube root. So it's okay to be negatives. So the domain of R here, because it's an odd root, there are no restrictions. It's going to be negative infinity. Oops. Negative infinity, comma, infinity. There. Okay? And then finally I have this little h of x equals the square root of x plus 5 over x squared plus 5x minus 14. So I have a radical and a fraction, and the radical this time is not in the bottom. So what does the fraction part say? Well, if I want to find the domain of little h, that's of little h here, then I need to do x squared plus 5x minus 14 cannot be 0, but I have an and. That's an intersection in math. I mentioned that earlier. That's an intersection. I have an and. Not only does the bottom not equal 0, can equal 0, and I have a radical, and that radical, x plus 5, what? Has got to be greater than or equal to 0, right? And it's in the numerator. The equal to part's okay here. So greater than or equal to 0. So when I do this, well, I'm going to factor this one. Let's see, x and x. So we have factors of 14 that subtract to give me 5. That's going to be 1 and 14 or 2 and 7. So 2 minus 7 is 5. They've got to subtract to give me 5. Again, if you have trouble with that, list method video. So we got 7 and 2. The signs are different. Bigger number gets a positive. So it doesn't matter where I put the 7 and 2, but the 7's got to get a plus, the 2's got to get a minus. And then I'm going to set both of those things not equal to 0. And again, I was told to use a NOR, so I'm going to do that. So every number in the world but negative 7 and 2 is okay. So if I drew a number line, if I drew me a number line over here, let's see, I'm going to find me some space here to draw me a number line. Then I take negative 7 and I take 2, and I basically knock them out. All right, so I'm just going to mark them right now because there's not really a way to knock them out on a number line. You don't show them, I guess, open circles if I wanted to. So I guess if I wanted to put an open circle on both those, I could. Right? And then what about the other part, the and, this other part? So the intersection. So everything except those 2 points is good, but it has to intersect with whatever this other one is. So I'm going to subtract 5 from both sides and get x is greater than or equal to negative 5. So now I have negative 5, which is in between the two, and it's only going to be this way. All out here. Okay? So where do those two things intersect? Well, everywhere there's green and what's not marked out with the blue. So it's everything this way except you can't have that point right there, right? So how do I do that? Well, what we're going to do because of that, remember we do the chain link together with parentheses. So the way we write the interval notation is going to be bracket, negative 5, comma, up to what number? 2. 2 with the parenthesis, union, chain link it back up all the way to infinity. Why don't I go out here to negative 7 or negative infinity? Because I've got to intersect them. That only goes here. So everything over here is already marked out because it doesn't have green. It's got to have green and not be marked out with blue. All right. So my domain here is negative 5 comma 2 union 2 to infinity. All right, and again, that was part of the and beyond part. Okay, the last three of these were just a little bit more than just, oh, let's just go figure this out because it's pretty simple. When I say pretty simple, I mean you got to identify what it is before it's simple at all. Okay, so you have to identify what it is, and we all know from algebra that the book, the teacher, the software, whatever, we can make it as complicated as we want to make it. Okay, we can do that. So I'm just trying to give you one here that's relatively complicated, the and beyond part here. All right. So hopefully this helps with finding domains. All right.